welcome to Unit 9. And we're going to take a look at Lesson 9.1 here. Got a whole bunch of different topics we have to do, but it'll set you up for some good success later on down the road. We're going to talk about some definitions for series, some terms that you'll need to know. We'll talk about one specific type of a series called a geometric series. You might have learned that in pre-calculus, maybe not. And we'll also talk about something called the nth term test. All right. Now, we're going to do some review stuff first, and I hope you remember doing this in pre-calc. If you haven't, then hey, you get to learn it here. Something called a factorial. So this is the notation for factorial, n with an exclamation mark, n factorial. And really what it is you're just taking that number n and you're multiplying it by every number before it until the number is like 3, 2, 1 at the end. Remember, n has to be a whole number for this to work out. And so with that in mind, we have n times the number before it, n minus 1, the number before that, n minus 2, n minus 3, and then once again, do all this until like 3 times 2 times 1, so you always end up with 1. So if I ask you to simplify this expression, n plus 2 factorial over n factorial, hopefully you can see that the n plus 2 factorial just means I start with the factor of n plus 2, and I'm going to multiply by each of the numbers before it. N minus 1, what's 1 before, sorry, n plus 1, and then what's 1 before that? That would be, yeah, just n, and then after that, n minus 1, n minus 2, and you're doing this all the way to pretty much the last number, 3, 2, and 1. If I'm dividing this by n factorial, remember n factorial is just n times n minus 1, n minus 2, all the way 3, 2, 1, and since this is all multiplication, goodbye. Yes, you're just left with n plus 2 times n plus 1. And that's what that equals to. Okay? So you're going to use this factorial notation very soon in Unit 9. So I want you to have a good idea of what it is right now. Okay, now let's talk about series. What is a series? Yeah, it's just the sum of a whole bunch of numbers. Okay? And then we have a more interesting term that we'll see in our course. An infinite series can really be represented by this lovely notation, the sum of n equals to 1 to infinity, where n is going to like infinity, it never stops, of the expression a sub n, which really means I'm taking a sub 1, or your first term, and adding it to a sub 2, which is your second term, adding it to a sub 3, your third term, and on and on and on to your nth term. And then because this goes on to infinity, you're going to go ahead and keep going and going and going. Okay. So we need to understand that when I have a sum to infinity, when I have this infinity symbol up top, this is an infinite series. Okay. So in example number 2, can I just ask you to write out the first 5 terms of this series for me? So what I have here is the sum of n equals to 1 to infinity. So yes, it is an infinite series. And the expression that we're going to use to express our values, or each of the terms, is given by this expression n over n plus 1. So we'll start with the first term, n equals to 1. If I plug it in, I get 1 over 1 plus 1, which is 2. Good. I have the next term, n equals 2. I'm going to plug that in. That'll be 2/3. And then it says the first 5 terms, so I'll just keep doing that now. And here's my 5th term. And if you left it like that, I'd be like, well, that's not really equal to that because it says it's the sum to infinity. So this keeps going and going forever. So I like you to put a plus dot dot dot. Okay, very important. Plus dot 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 to show that it goes to infinity. All right. So understanding the summation symbol and being able to write it out as a long expression is very important. Here are some other examples of what I need you to do with infinite series. Can you actually go ahead and write an expression for the nth term? So really what I'm saying is, can you write down what we had over here? Let me circle that in purple. Remember this thing, that expression, n over n plus 1? That's what I want you to do over here in questions 3 and 4. So just looking at the terms, can you come up with an expression that describes each of the terms? So you think about this, this would be n equals to 1. And this here is n equals to 2. And this here is n equals to 3. And do you see anything interesting about those numbers in the denominator? Yeah, I hope you see that the first term is just 1 over 1. Second is 1 over 4, which is 2 squared. 1 over 9, which is 3 squared. And so hopefully you can see that the nth term is actually written as the expression 1 over, you guessed it, n squared. Excellent. Can you try number 4 yourself? Numbers 1, 2, 6, 24, and 120. Don't know if you know what those are, but that's just 2 times 1. 6 is 3 times 2 times 1. 24 is 4 times 3 times 2 times 1. And 120 is 5 times 4 times 3 times 2 times 1. If you're thinking factorial, I agree. 3 over n factorial. Yeah. So that was just to write the expression for the term. Now I want to extend it to write an expression for the following series. So this is where I need you to add in that summation notation because number 5 and number 6 are infinite series. So really, I just need to go this. Sum of n equals to 1 to infinity. And just like examples 3 and 4, you need to come up with an expression to describe each of these terms. 2, 4, 6, 8. Who do we appreciate? I think those are just even numbers. And to represent even numbers, where this is n equals to 1, n equals to 2, n equals to 3, n equals to 4, I think we just have 2n. How can I find an expression to represent the denominator? Terms seem to be odd this time. 2n. Oops, that's too much, right? 2 times 1 is 2. Gotta subtract 1. And there you have it. Done. Take a look at what's happening with number 6. What's the pattern going on here? Hopefully you can see that I'm multiplying by -3 each time to get to the next term. Hmm. 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 So there's a few ways you can do this. If you want to think about this as the first term, and then here's the second term, and here's the third term. It looks like to go from the first term to the next term, we have to multiply by 3. So let me just go ahead and start this off. The sum of n equals to 1 to infinity. And I have here 2, because I'm starting with that, times, and I guess I have to multiply this by -3, but if you think about it, I only have to multiply by one -3 to get to the second term. So if I left this as just n, that wouldn't be the actual correct expression, right? Think about it. If I put in 2 for n to give you the second term, -3 squared is 9, 9 times 2 is 18. Ooh, that just actually gives me the third term. Oops. Change this to n minus 1, and we're good. Okay? Now, if you didn't really want that n minus 1, you could have written this another way. You could have just said, okay, well, I'll just leave this as n. Okay? But if you did that, you shifted it. You went one more, which means I think you need to actually shift this down to 0. So if I did it like this, when I plug in 2 times -3 to the power of 0, -3 to the power of 0 is 1. Now I get my first term of 2. So if I went and started my sequence with this as n equals 0, and then this other one is n equals to 1, and so on, then the blue expression is good. Okay? So it just depends on how you start counting. N equals 1, n equals 0. Okay. Okay. So now in example number 7, I'd like you to take a look at this. We've got a sequence start to n equals to 0 to infinity of the expression 2n plus 1. And this time when I plug things in, I get, hey, the values of 1, right? This is when n equals to 0. N equals to 1, so 2 times 1 is 2 plus 1 is 3. 5, that would be when n equals to 2, n equals to 3, and so on. It says show a sequence of partial sums. What do I mean by partial sums? Well, if I were to sum the first term, that's a partial sum. Yeah, I know it's just 1, but yeah, it's a partial sum. And I can ask you to sum the first two terms. That would be 1 plus 3, 4. I could do S sub 3, which is the sum of the first three terms, another partial sum. Yep, 9. See this? And so on, right? And so on and so forth. So my sequence here for partial sums are the numbers 1, 4, 9, 16, 25, and so on. Okay? Now notice that this sequence of partial sums looks like it approaches infinity because it just keeps getting bigger and bigger and bigger and bigger and bigger. So when this happens, when the sum approaches infinity, we have this terminology called the series is divergent. Okay? Getting bigger and bigger and bigger, diverges. Okay? Now, converse to that, we have an example number 8. So looking at example number 8, I'm going to ask you to write out the terms and start doing the partial sums. Okay? And let's see what happens here. So when n equals to 1, I get 3 over 10. When n equals to 2, I get 3 over 100. N equals to 3 is 3 over 1,000, and so on and so forth, right? And if I look at my sums, my partial sums, well, taking the first term, it's just 0.3, right? That's 3/10. If I add the first two terms, that would be 3/10 plus 3/100, so it would be 0.33 or 3300. If I take the third term and add that together, I get 333, and so on and so forth. You'll see I just keep adding 33333s. And what do you think this is as a fraction? You bet, it's actually equal to 1/3. So interestingly enough, even though you have infinite terms, so when n goes to infinity, you have infinite terms. What happened to your sum this time? The sum wasn't infinity. The sum was finite. It actually was a nice number. It ended. So when you have this case when the sum is finite, we have a special term for that. It's a convergent, and this happens to be a geometric series, so a convergent geometric series. Now, why is this one called a geometric series? Yes, one last terminology for this page. It's called a geometric series because if consecutive terms in a series have a common ratio of r, meaning to get from one term to the next, you're multiplying by the same number, then this series is called a geometric series. Okay? In our previous series here, what number were we multiplying every single time? Well, to go from 3/10 to 3/100, we multiplied by 1/10. To get to 3/1000, we multiplied again by 1/10. And so in that particular series, our R, or common ratio, was 1 over 10. Okay? Now, if the geometric series converges, it is possible to find the sum even though it has infinitely many terms. Okay? So let me show you how I can prove this to you. Well, here we go. Looking at this sum, let S stand for the sum, right? The sum of a geometric series. And I'm assuming that this series converges. Okay, so I do have an assumption here that this does converge. Okay, if I were to multiply that series by R, okay, you see I'm taking every one of these terms and multiplying by R, so A just becomes AR becomes AR squared becomes AR cubed, and so on, right? And Remember, this is an infinite series. This goes forever and ever. So now if I were to actually take these things and subtract, okay, like if I take S minus RS, that's how I get this, S minus RS on the left side of the equal sign. What happens now if I subtract is I get A, but AR minus AR, that just becomes 0. AR squared plus AR squared, if I subtract those two things, it becomes 0. This all becomes 0. So I'm really just left with the value of A. And noticing if I were to factor out the S from the left-hand side, I get S equals to, or sorry, X times 1 minus R. I can solve for S, and yeah, I get this lovely formula of A over 1 minus R, okay? Where A represents the first term, and R is the common ratio. What happened there? Common ratio. And once again, this is of a geometric series. And maybe I should say convergent series, okay, to be more exact. Okay? So it's really cool that we have a nice formula. As long as we can find A and we can find R, we can actually get the actual infinite sum and write it as a finite number. Crazy, eh? And so on the next page, we've summarized this into a box. Yes, everything in the box is important. And we have also something called the geometric series test. Okay? The sum for a geometric series, okay, is equal to A over 1 minus R, provided that we need to understand that the thing must converge. And how do I know if something converges? It all really depends on that R value, the ratio. If the ratio is less than 1, which was the example that I gave you over here, remember? This ratio here was 1/10. Example number 8, it's less than 1. We got a converging series, okay? And if the ratio is bigger than 1, like if something doubles or even equal to 1, right? It's just like the number 3 plus 3 plus 3 plus 3 plus 3 forever, then these two situations show that the series diverges because you're going to get an infinite sum, okay? So once again, if it diverges, your sum is either going to be what? Infinity or negative infinity. And if it does converge, well, we have a formula. We know that sum is equal to A over 1 minus R. Okay? And this sum infinity means that there's an infinite number of terms. So n equals to infinity. All right? So looking at this next set of examples, I'm going to ask you if the series converges or diverges. And if it is possible, meaning if it converges, find the sum. Now, it might be hard to figure out R right away by looking at these things, but if you can look at it and just figure out, do it. If you can't, my suggestion to you is to actually write out the first 2 or 3 terms. And hopefully by writing out the terms, you can actually pick out what the common ratio will actually be. So for number 9, if I would write out the terms, when n equals 0, I have 3 over 2 to the 0. I guess that's just equal to, well, I guess I write it out 2 to the 0, just so you can see it, right? 2 to the 1, 2 to the 2, and that's, of course, going on forever and ever. So this is 3 plus 3 halves plus 3 quarters, and so on and so forth. And then can you figure out what R is going to be if you compare two terms? I hope you can see that the R value here is equal to 1/2. And since the absolute value of R is less than 1, we know this converges by the geometric series tests. And sometimes you can use the short form GST. Okay? And yes, you should be able to find the sum. So the sum of an infinite series here would be equal to the a value, which in this case is 3, over 1 minus r, which is a half. So 3 divided by a half, this sum is equal to 6. Okay. So can I get you to try 10 and 11? So press pause now so that you can try it yourself, and then come back and double check your answers. Press pause. 3 halves to the power of 0, 3 halves to the power of 1, 3 halves to the power of 2. Hopefully you can see that I'm just multiplying by 3 halves every single time. So my common ratio here is actually equal, I should say just r first of all. The common ratio is equal to 3 halves, and so therefore the absolute value of that is bigger than 1, which means this diverges by the GST. And since it diverges, that's right, no finite sum. Good. Final one here. Ooh, interesting, there's a 4 in front. Don't freak out, just keep it. 1, 2, 3. I think this becomes -2. This becomes 1. This becomes minus a half. Oops, what did I press? Don't forget plus dot dot dot. I forgot that from the previous one here too, plus dot dot dot. And here, I hope you can see that the r is equal to -1/2. And since the absolute value of that is still less than 1, this converges by the geometric series test. And yes, we can find the sum, where the formula is a over 1 minus r, -2 divided by 1 minus, and be careful here, this is 1 minus -1/2, which is 1 plus a half, which is 3 over 2. Dividing, we can multiply by the reciprocal, so -4 over 3. Done. Okay, so look at this repeating decimal. Oh, repeating decimal, what does that mean? That means it goes on forever, you're right. Okay, how would you rewrite this as a fraction? That's what they're wanting to figure out. Well, I guess we should really think about what this means, right? 0.08 repeating. I guess that's really 0.08 plus 0. Well, 0008. And then I guess we have to do that 0.000008 and so on. If you think about this as a fraction, this is 8 over 100. This would be 8 over 10,000. That 8 over, add 2 more zeros, a million. You bet. And I hope that you can now see that the common ratio is equal to 1 over 100. And since the common ratio is bigger than 1, we know this converges by the geometric series test, and therefore we know that the sum is equal to the first term all over 1 minus r. And yes, you can find this out quite nicely, that the first term is 8 over 100, and r is 1 over 100. So interestingly enough, this becomes 8 over 100. 1 minus 1 over 100, that'll be 99 over 100. And voila, the answer here as a fraction is just 8 over 99. Cool, eh? All right. So it's pretty cool that all these things form a geometric series that converges. Nice. Okay. Now, let me throw in a twist, unfortunately for you. Number 13 gives you this series, and I know this is not geometric, so that's fine, but noticing this expression here, if I were to write out the terms, look at this. I get 1 over 1 plus 1, which is really 2. And the next one is 1 plus a half, so that's 1 and a half. And the next one after that is like 1 and a third, so 1.3 repeating. So you'll see that, you see these terms actually kind of get smaller and smaller and smaller. So you might be thinking, oh, the R value is actually less than 1, so therefore it must converge. But this says, no, it does not converge. First of all, this is not a geometric series because the common ratio is not always the same. So get that out of your head. Okay. The second thing here says, can you show the sequence of partial sums? So sure, I'll do that. The sum of the first term is just 2. Easy. The second one, 3.5. Not that bad. Adding 3 of them together, that's like 4.83 repeated. Okay. Adding the fourth one together, I know you don't do this, but I could do it on my calculator. It's 6.083 repeating. So it looks like the sum increases, but these terms, they get smaller and smaller. So shouldn't you be adding like 0 sooner or later? So I want you to realize this. A series cannot converge unless the terms approach a limit of 0. Okay? You'll see that this term that we have here, or this series, this, if I keep going further and further, doesn't actually approach 0. Because the smallest this could be is 0. Oops, I should make this a little bit nicer. The 1 over n, that's small as this can be 0. So 1 plus 0 is, yeah, 1. So in the end, you're pretty much adding bits like 1, 1, 1. And if I keep adding 1, of course this sum will never actually converge. So that leads us to this lovely test called the nth term test. But this is only for divergence, okay? Only for divergence. It doesn't say anything about convergence, okay? All it's saying is this. If the limit as n approaches to infinity of the term does not equal to 0. So once again, back to that previous summation here, right? Look, at the ends, when n approaches to infinity, if it's not 0, then we know that the series must diverge. If it does equal 0, well, we can't say anything. Okay? So only if it's not 0, we can guarantee it diverges. If it does equal 0, stay tuned for the rest of the unit. Okay? So now, as our last example, if I ask you to show that this thing diverges, what you can do is really just take the limit as n approaches to infinity of the a sub n term, which is the expression. Okay? So take the expression n factorial over 2n factorial plus 1. And I'd like to ask you to evaluate this to see if this actually equals to 0 or not. Well, by the end behavior model, I hope you can see that I don't have to worry about that plus 1 because the factorial is huge. And then, of course, these factorials just divide out. So you're left with the limit as n approach to infinity of 1/2, and that equals to 1/2. And that, of course, is not 0. So therefore, by the nth term test, and you please quote the test, by the nth term test, this diverges. Okay? We know this will never have a finite sum. It's going to be equal to infinity. All right? So welcome to the beginning of Unit 9. Lots of different terms, but you'll hear them quite a lot in this unit. So study this one well, do the practice assignments well, and let's come back for lesson 9.2. Until then, bye for now.